Okay, so after finishing section 3.9 related rates, now we're going to talk about something totally different in 3.10, linear approximations and differentials. So basically, we're going to talk about using linear. Remember, linear is f of x equals mx plus b, linear functions. So how do we use a linear function to approximate curves? Because it's easier to deal with linear than curves. And then we're going to discuss differentials and how these two are interconnected. So just to give you an idea before I start, if you have a curve and a tangent line to the curve at a point, that's just a of a. So we can easily find the equation of the tangent line. We know how to do this as long as this is differentiable. So once we find the equation of the tangent line, which is going to turn out to be like this, then we can use it to approximate the y values f of x at any point near a. As long as you're close to a, then the approximation is almost, the same. So it's very close. That's what this. Once you go away from a, then you can see the difference between the linear value and the actual value. Okay. So again, what's the equation of the tangent line as we know it? Of tangent line, equation of tangent line, graph of f. So if this y equals f of x at the point a f of a, it's y minus y1 equals m, which is f prime at a into x minus x1. So y equals f of a plus f prime of a x minus a. This y, we use L of x for that. This is called the linearization of the function f at a. Okay, linearization of the function f at a. So the approximation f of x is roughly f of a plus f prime of a x minus a is called the linear approximation, which we denote by L of x. It's called linear approximation or tangent line approximation of f at a. So this value is the actual value with respect to the line. If we want to use it for the curve, it's an approximate value. Okay, that's what's equal here, because that's the equation of the tangent line. This is the y value for the curve. The y value from the curve is approximately equal the y value from the tangent line, as long as you're close to the point of tangency. Let's see an example about that. Number 6, page 258. We're given g of x equals cube root of 1 plus x. And let's go see what they want. Page 258, number 6. It says find the linear approximation of the function g of x equals cube root of 1 plus x at a equals 0. And use it to approximate the cube root of 0.95 and the cube root of 1.1 and illustrate by graphing g and the tangent line. Okay, so to find the linearization or the linear approximation, g of x is roughly g prime of a plus, g of a plus g prime of a x minus a. So g of 0 plus g prime of 0 x minus 0. Well, this is 1 plus x to the 1/3. So g prime of x is 1/3, 1 plus x to the negative 2/3 times derivative of 1 plus x is 1. So 1 g prime at 0, if you put a 0 in there, you get 1 to any power is 1 times 1/3 is 1/3. and g of 0 is 1. So g of x, which is L of x, this is roughly that, and this is your L of x, the equation of the tangent line. And it says use it to approximate the cube root of 0.95. So if you want to use cube root of 0.95, you gotta match it with this. It's cube root of 1 plus x. So x has to be negative 0.05, right? 1 plus negative 0.05 is gonna be 0.95. So the cube root of 1 plus x, it's roughly 1 plus 1/3 times negative 0.05, which is, if you do the math here, it's 0.983. Repeating, if you want to do cube root of 1.1, that's cube root of 1 plus 0.1, so that's your x, which is roughly 1 plus 1/3 times 0.1, which is roughly 1.03. And you can look at my work with the graphing calculator. There's a chart there, just follow that, okay? This is what I'm talking about in the notes. So I did all these values of x, f of x, the actual values, and then the approximate values, okay? The f of x you get by plugging in the values into the original equation. L of x you plug it into the tangent line, and you can see the difference between the actual and the original. And as you go away from, as you move away from 0, because 0 is the point of tangency, your discrepancy gets bigger. As you get closer to 0, your discrepancy is very small, okay? Now to differentials. So okay, I want to show you the page 58 star, because I don't want to keep writing everything. On 58, page 58 in the notes, let y equal of x, this is what I'm talking about, be the equation of the function, and y equals f of a plus f prime of a x minus a, the equation of the tangent line, which is L of x. Okay, we're familiar with that. So we define delta y, which is the actual change in y. Delta, so you have a and a plus delta x. Delta x is the actual change in x. So of a, you get f of a, x plus delta x, you get f of a plus delta x. That difference between y2 and y1 is the change in y as we know it, and that's relative to the curve. Now if you look at the difference relative to the tangent line, we call it dy. Okay, that's what dy is, differential in y. And this is delta x and dx are the same. That doesn't change because the change in x is the same whether you're using the tangent line or the curve. Okay, one more time. So if the point of tangency is at a f of a, we draw a tangent line, we can find the equation of the tangent line, we can find the equation of the tangent line, that's what we call linearization. We define delta y, the actual change in y, which is f of x plus delta x minus f of a plus delta x minus f of a. dy, however, is the estimate change in y because it's relative to the tangent line, which is this piece, and this is dx or delta x. The actual or the approximate change in x are the same. Okay, now remember, slope of the tangent line, this is the tangent line, slope is rise over run. That's what it is. F prime of a is dy over dx. That's why we can write dy is f prime of x dx or f prime of a dx. That's where this came from. If you're wondering where that notation came from, that's what it is. Okay, remember slope is rise over run. So slope is the derivative at the point. Delta y or dy over dx. That's where this came from. Okay. So delta y is roughly dy. The closer you are to the point of tangency, the smaller the discrepancy. That's why we can say. So remember, delta y is f of x plus delta x minus f, or f of a plus delta x minus f of a. dy is f prime of a dx. So delta y is roughly dy, which is f prime of a dx or delta x, it doesn't matter. Okay, so dx is called differential in x, differential in x, and dy is called differential in y. That's what we mean by differential. So that piece I showed you on the graph. Okay, and so we know that delta y is roughly dy, which equals f prime of x dx, or f prime of a, whatever you're using. If you're using a specific value, it's a. If you're using general value, it's that. Okay, so let me ask you this. So when we say find the differential, okay, so if I say find the differential dy, and I don't give you values, okay, where y equals ln of sine theta. Now we know how to find dy by dx, which is the derivative, right? So let's do that. What's ln of u? It's u prime. It's u prime dy by d theta, I'm sorry. It's u prime over u, which is cosine theta over sine theta, which is cotangent theta. So dy by d theta is the derivative. If they only want the top, all you have to do at this point is times by d theta. So dy is cotangent theta d theta. If they give you values, you can plug in, but if they ask for differential, you'll find that piece that I showed you on the graph without plugging in any number, and that's called the differential, okay, in y. Part B, if y equals e to the x over 1, same thing. To find the differential in y, we do derivative first. Quotient rule. So we do g, which is the bottom, derivative of the top, which is e to the x, minus e to the x. Derivative of the bottom is negative e to the x over 1 minus e to the x squared. So if you work it out, distribute that, so you get e to the x minus e to the 2x plus e to the 2x, which cancels out. So dy would be, if dy by dx is this, so dy is all this times dx. And that's called the differential in y, okay? That's called dy or the differential in y. Okay, now let's look at page 259, number 20. Page 259, number 20. It says, find the differential and evaluate, so they were going one step further, evaluate dy for the given value of x and dx. Good. So first it says find differential cosine pi x, so let's do that. Dy by dx is derivative of cosine u is negative sine u, which is pi x, times derivative of pi x is pi, so it's negative pi sine pi x. I always put the number in front of the sign, so that's dy by dx. So dy is negative pi sine pi x dx. That ends the first part, and then the second part, it says find dy for the given values of x. So what is x that we're given? X is 1/3 sine of pi over 3, and dx is negative 0.02. So you can plug that in your calculator and get the answer, okay? Number 24. Page 259. Y equals x minus x cubed. Same thing. So we're going to find... No, that's not the same thing. Let's see what they want. It says compute delta y and dy, and then sketch a diagram like figure 5 showing the line segments with... Okay. So what is delta y? Delta y is f of x plus delta x, just like I showed you, minus f of x. We're given that x is 100 delta x, which is always dx, is 0.5. So that's f of 100 plus 0.5 minus f of 100. So if we put those numbers in, f of 100 0.5, f of 100.5, oh, I'm sorry, that's 24, x is not that, x is 0. I copied this from 84, sorry. And delta x is negative 0.3. Okay, let me do this over. I don't want to confuse anybody. Not yet, at least. 24, page 259. Y is x minus x cubed. X is 0 and delta x is negative 0.3. So to find delta y, it's f of x plus delta x plus delta x minus f of x. So f of 0 plus negative 0.3 minus f of 0. So if you plug that in, you have calculators, you can do that. Negative 0.273 minus 0. So delta y is negative 0.273. That's the actual change, and actual means relative to the curve, not the tangent line. dy, the estimate change y, which is relative to the tangent line, is f prime of x or f prime of a, it doesn't matter. So the derivative is 1 minus 3x squared. So this is f prime of x. We're going to do f prime at 0. It's 1 minus 0, which is 1. And then dx, which is negative delta x, which is negative 0.3. So negative point. Okay. So we found dy and we found delta y. They're not too close, but they're enough. 34. Page 259, number 34. It says use linear approximation to estimate the given number. So how do we estimate using linear approximation? You cannot just put this in the calculator and give me an answer. It's going to be 0 if you do that. So the function is obviously square root of x, and this is 100 plus 0.5, so this is x and this is delta x. Okay, so we want to, so remember what we talked about, L of x, which is an approximation to find. So we know that f of x plus delta x minus f of x is f prime of x then times x minus a. Okay, so we want to find f of x plus delta x, or this, it's f of x. We used a, it doesn't matter, a plus f prime of x, or a x minus a. Okay, f prime, and this is my dx. So basically delta y is roughly dy. That's what we're using. So square root of 100.5 is roughly f of 100, square root of 100, plus the derivative of square root f prime of x is 1 over 2 root x, which is at that point it's 1 over 2 root 100, because x is 100, and dx, which is delta x, which is what, 0.5, 10.025. Then you can check your work with the calculator. Okay, you can use the dx here. That's what I used. I don't want to confuse you here. So all you always use delta y is roughly dy. Delta y is f plus delta x minus f of x, and y is f prime of x dx. That's where this came from. Okay, and I always like to ask a question similar to this on the test. So this is a hint for those of you who are watching the video. Okay, the last part of this section is about error. So if x is the measured value of a variable, so you bought a desk for work, and then you measured the width of the desk, That's your x, the mid value. X plus delta x is the exact value of the variable. So you look in the paperwork that you got for the desk, and it tells you the exact width should be 50 centimeters, but when you measure it was 50.5. Okay, so your measured value, the exact value. So the difference between measured and exact is the error, because there's always a margin of error when you measure anything. Error in measuring the variable. Also, when you do f of x plus delta x minus f of x or delta y, this is the maximum. It's called maximum error in y, in measuring y. And if you do delta y over y, it's called relative error in y. Now these are exact values. Why exact? Is using delta y. If they want approximate values, remember, approximate, you're using the tangent line, so using dy over y, which is the estimated relative error. Okay, so 42, page 259. Remember, anything with delta is exact, anything with d is approximate. Okay, if we do delta y, it's exact values, or delta y over y. If you do dy, it's approximate, dy y is approximate. Keep that in mind. So 42, page 259, the radius of a circular disc is given as 24 centimeters with a maximum error in measurement of 0.2. So dr, because if r is 24, then dr is 0.2. Use differentials to estimate the maximum error calculated area of the disk. And they want estimate. When they say estimate, that means they are looking for d, not delta. So what is it that they want to estimate? The maximum error in calculated the area. So they want dA. Okay, area of a disk. Remember, the formula says A equals what? Pi r squared. So to find dA, we do dA by dr first. It's going to be 2 pi r. So dA is 2 pi r dr. 2 pi, r is 24 and dr is 0.2. So the maximum error in estimating the area is 30.2 centimeter squared. You look part B, it says what's the relative error and the percentage error. So relative error, again, it's estimate. Relative error is dA over A. dA is 30.2. Found that. Area is pi r squared. That's the relative error, which is 0.016667. The percentage would be 1.67%. And that's it for 3.10, and that's it actually for chapter 10.